Electric field strength in a region of space can be understood two different ways. One is just by mathematical calculation that you have completed. How to find electric field or where electric field strength going to be zero. All these things you have calculated mathematically. In past few sessions, I have explained in details how to do it with mathematical calculation. But there is another very convenient way to understand electric field or its strength, that is by drawing electric lines of forces or electric field lines. Hello everyone, MKS here. This session I am going to discuss electric field lines or electric lines of forces in details. So stay tuned till the end of this session. Today I am going to explain the way past 3 decades of my teaching career I have explained electric lines of forces to my students. Step by step, I'll explain what is electric field line, how to visualize electric field at a point. First, let us know what are electric field lines. Literal meaning of electric field lines are a visual representation of electric fields. Electric field lines are imaginary lines in a given space-time along which a free positive charge moves. So field lines what? Imaginary lines along which in a given space-time a free positive charge can move. They help us understand the direction and strength of electric field around charged objects, and Michael Faraday, the genius, introduced the concept of electric field lines. Before we start visualizing electric field, let me explain the way Faraday explained electric field lines drawing in his book. So you know the strength of electric field due to a point charge at a point can be found by the formula. If there is a charge Q at a distance r from it, you can find strength of electric field by using the formula kq by r square. R cap is the unit vector joining the charge to this point P. If this is the source charge which is positive and your test charge is always positive, you know, then in what direction the test charge will experience force? That force going to be radially outward. Okay? And if you move far away from this point charge, the strength gradually decreases. Faraday suggested to draw the electric field lines in that direction only, where a vanishingly small test charge or unit charge or a charge compared to this charge Q will move. So if you take the point charge Q here and try to draw lines of forces, then electric field strength, we will remember it is stronger nearby points. So you make big arrows, gradually arrow length is reducing, and then at infinity the arrow length will be reduced to 0. Similarly, it can be drawn this manner also. Any direction, it can be drawn isotropically. Isotropically means can be drawn in all directions. It is symmetric. And I am not taking many field line, many directions, because the number of field lines actually depend on the amount of charge. So how we don't know how much charge is there. We have just taken one charge which is Q. So let us take 4 electric field lines by obeying Faraday's rule. Faraday, what he suggested, that we are going to follow. If we go far away from this, the gradually length of this arrow is going to be reduced. Finally, if we join all these arrows, we get a electric line of force. Okay. So electric line of force will be directed radially outward, this direction. Here also it will be radially outward, directed this way, radially outward, directed this manner. Radially outward. We have taken 4, I told you, because we don't know magnitude of charge. It depends on the magnitude of charge. These are electric lines of forces. 4 electric, if the magnitude of charge large, then field lines can be drawn this way also. Okay. But you should remember that lines of forces will come out symmetrically, and isotropically it can be drawn in all directions. Okay, in all directions. There is no chance that in towards left it will be less and towards right it will be more. So these are field lines due to a plus Q charge, that is, along which a charge, a positive charge, can move if it is free to do so. If you just attach it over there by using a glue, that positive charge will move. But if it is free to do so, it will follow the direction of electric field lines. Okay. Now if we try to draw due to negative charge, how do you draw it? It is radially outward for positive charge. If you are going to do it for a negative charge, say minus Q charge, then we have to consider the direction in which a positive charge will experience force when it enters the electric field of this charge. It is obviously towards the charge. So electric field line due to minus Q charge will be inward. And this also can be drawn isotropically. It means in all directions. Okay. I am taking 4 lines of forces here. There is no choice. From a charge, many lines of forces can come out. You can take more also, doesn't matter. But remember, it should be drawn isotropically. In all directions, it can come out. So minus Q charge, it's a point charge. Towards minus Q, the electric field lines will be directed radially inward. This is the direction of electric field lines due to negative charge. So how can you visualize electric field? By drawing electric field lines. Field lines allow us to visualize electric fields. Just to have seen, those imaginary lines will tell us the direction of field you take inward. You take outward. That field will be radially outward. And if it is a negative charge, the field line will be radially inward. You take field line radially inward due to negative charge. So this tells us the direction of electric field due to one positive charge, due to one negative charge. Now, these field lines can be drawn due to 2 isolated positive charges, due to 2 isolated negative charges also, and due to 1 isolated positive charge and 1 negative charge. Okay. So, field line will allow us to visualize electric field. The picture, this will picture the attraction between unlike charges that I'll show you, and repulsion between like charges. Field is there means positive charge will move that way. But if you keep 2 positive charges side by side, they will try to separate. So field line will exert lateral pressure on each other. They will move. That we'll see. Now what is the origin and termination of these lines of forces? Actually, same thing I am repeating here. Electric field lines always originate. This I am generalizing. What I told you here, what we have realized with the help of concept of electric field strength at a point, that we are generalizing here. Electric field lines always originate from positive charge and terminate at a negative charge. Number 2, they do not terminate in the space around the charge. You have seen in this example, charges are moving, field lines are going away. Where are they going? They will not terminate anywhere. They will terminate at infinity. So in the region of space, in the surrounding of this point charge, there is no scope of limiting the electric line of force. It will continue till infinity. But if we have a positive charge and a negative charge, that I am discussing here, it will be originated from positive charge and will be terminated to the negative charge. If you have taken plus Q charge here or Q1, whatever, and this charge is minus Q1, then field line will go this way, positive to negative. Otherwise, situation is as before. I am taking just 3 lines of forces. Number of lines of forces depend on the magnitude of charge. So in this case, lines of forces will continue till infinity. Here lines of forces originated from positive charge and terminated at negative charge. This you should remember when you are drawing electric lines of forces in complex situation. They will never terminate in the space around a positive charge. Around a charge, positive or negative, doesn't matter. It will never terminate. Okay? Specifically for isolated charges, field lines come out of a positive charge, terminate at infinity. That I showed you. When a positive charge is near a negative charge, field lines originate in the former and terminate at the later. Why do field lines behave this way? Due to positive charge, I have already explained. Due to positive charge, another positive charge will experience force of repulsion, will go away. Due to negative charge, positive charge will move towards the charge. Okay? So, if we imagine a positive charge creating an electric field around it, then you have to keep in your mind the region of space in the surrounding of this charge is filled with those field lines, nothing else. This positive charge will create electric field lines in its surroundings. Okay? Field lines represent the direction in which positive test charge would move if placed in that field. That is already explained. And like charges repel, field lines point away from positive charge. Negative charge nearby field lines lead towards it due to attraction. So this you understand why field line will be directed from plus Q1 to minus Q1. Because on this field line, if we keep a positive charge here, that positive charge will be another positive charge smaller than this. Q1 will repel it and Q2 minus Q1 will attract it. So it will follow this path. Follow this path means it will follow path tangential to it. Okay? Field line, it will follow this curved path, but field will be directed tangential direction. E will be directed tangential. Okay? Electric field will be directed tangential. Field line will go from positive to negative charge because by definition, a positive charge will move along the field line if it is free to do so. So it will always go from plus Q1 to minus Q1. That's why field line also will be directed from plus Q1 to minus Q1. Now, like charges repel, field lines point away from positive charge. So, if we keep a plus Q charge here, identical plus Q charge here, this identical charge will also create electric field in its surrounding. but this charge will repel it. That will be understood. I told you, when you are pictorially representing the electric field, then you have to understand electric field lines. Then you have to understand everything with the help of those field lines. So this has field line, it is trying to come this way, but field line due to this is repelling. So those field lines repelling means the field line created by this cannot move towards it. It is repelled like this. Here also it is repelled. It cannot reach towards left. It will be repelled. It will go this manner. This side also it will be this manner. It will go this manner. You can draw many charges like this. Situation will be like this. They will not meet each other also, because two similar charges always repel, and that is understood with the help of these electric lines of forces. Electric lines of forces are repelled this way. Or you can say that they exert a lateral pressure on each other. Exerting lateral pressure on each other. That's why shape of electric lines of forces will be like this. And another thing we have to keep in our mind, if this plus Q emitting 5 electric lines of forces, this one also will do so. This one also, because this is identical charge. I told you number of lines of forces proportional to the amount of charge, magnitude of charge. So two positive charges kept side by side, their direction of lines of forces will be almost like this. Many can be there this way also. It will be there, no? Positive charge can send electric line, field lines or lines of forces this manner always. Here also. They will not move towards left, will move towards right. So it seems that these field lines are exerting lateral pressure on the field lines created by this plus Q charge. Okay. So electric field lines due to 2 plus Q charge will be like this. Similar is the situation when you consider two negative charges by keeping them side by side. If you keep minus Q charge here and another minus Q charge here, just it will be repeated, but this time lines of forces will be directed towards the charge. Just arrow direction will be like this, towards the charge. Okay. It will be directed towards the charge always, as I told you earlier, radially inward. So here also field lines are exerting lateral pressure on each other. This arrow will not be directed that manner. It will be directed this way always, towards the charge. Never do this mistake. It will be directed towards the charge. Clear? There are many lines of forces there, but if you keep two identical charges side by side, it seems that they are exerting lateral pressure on each other. So here the length of lines of forces seems that going to be increased. But in this case, when we have taken one positive and one negative charge, it seems that the lines of forces, the field lines trying to contract. It is due to their attractive property. Okay, this is one of the property of electric charges. Similar charges repel, dissimilar charges attract. So if they attract, they have tendency to come close towards each other. So length of electric field lines going to be decreased. This is the concept. This way we can visualize electric field lines. We can understand what will be the direction of field line due to a charge, due to single charge, due to group of charges. Maybe 3 charges also there. I'll discuss with examples. Now, when you are plotting electric field lines like this, then a question arises. As I have told you earlier, electric field lines will show you the direction in which a positive charge can move. So automatically you have a question in this complex situation where a plus q, another plus q kept side by side, what will be? It will never be directed towards. This we should remember always. It is away. In this complex situation, question arises, do we expect field at this point due to this charge? Field at this point due to this charge? Of course, field strength exists. That field will be subtracted or added, whatever, that you can get vectorially. So let us see what is the direction of resultant field here. Due to this plus q charge, the field, you know, it will be radially outward, this manner. Due to this charge also, the field strength will be radially outward. Alright. Now, the resultant of, due to this charge, if we consider field is U1 and due to this charge field is E2, then resultant field will be directed like this. So, unit positive charge will move along the direction, or a positive charge will move along the direction of the resultant field. And this is the situation if you consider strength of electric field here. What will happen? By considering the resultant field strength, it will be like this. Why? Because due to this electric field will be directed this way, U1. Due to this electric field will be directed this way, that is E2. Their resultant U1 and E2 will go this way. Now we are going to draw one very important conclusion, that electric field lines, when it is curved, the tangential direction is the direction of motion of the charge. So if somebody tells you, some author, some books you have read that electric lines of forces are drawn in such a way that the tangent drawn to the field line at a point gives the direction of electric field there, then that will be appropriate. At this point, if we draw electric field, then it will be directed tangential direction. At this point, it will be directed tangential direction. At this point, field will be directed tangential direction. Okay? So, two important concepts we have learned so far. That field we are representing pictorially, can be represented pictorially. The tangent drawn at a point will give you the direction of electric field strength in case of complex situation. When two positive charges are kept side by side or two negative charges are kept side by side, situation will be like this. Even more complex situation. 1 plus 2q charge here, other minus 4q charge there. Can happen this way. You should remember that tangent drawn at a point gives the direction of electric field strength over there. Okay. So field in case of these curved lines will be tangential to the path. Now let us study some properties of electric field lines from the previous discussion, from the previous observations. Number 1 is very important, never intersect. What do you mean by this? Field lines never intersect. In this diagram I told you lateral pressure, all these things arising because there is force of repulsion. Field lines never intersect due to this reason. Field lines never intersect due to this reason, what I told you, that direction of electric field is tangential to the path. tangential to the direction of lines of forces. So if you think that two lines of forces are intersecting, contradiction, we are assuming that two electric field lines are intersecting this manner. This is a field line, okay? This is another field line. This we have drawn. Arrow you have to put. Along the direction of arrow, the positive charge will move. Maybe unit positive charge, maybe vanishingly small test charge, whatever. A positive charge will move. And this is one field line L1, this is the other field line L2. They intersect at this point. So what going to happen according to the definition, according to our observation, in the first line, the electric field strength is tangential direction. So electric field here directed tangential direction. Here electric field is directed tangential direction. So in a electric field, you are getting two direction of electric field strength. But EFS cannot have two different directions in the same field. It will have a unique direction. Because of this reason, they can never intersect each other. Understand? Next important property we are going to do, that is perpendicular to surface. What do you mean by this? This is another very important property. Field lines are always perpendicular to the surface. What do you mean? Why field lines should be perpendicular to the surface? Suppose we have taken a surface like this, not circle, surface of sphere. Field lines either will meet the surface or emanate out of the surface perpendicular to it. It has to go perpendicular direction. Field lines has to go in perpendicular directions. Has to be like this. Similarly, they may terminate to the same surface or another surface in perpendicular direction. This way. They have to meet the surface in perpendicular direction. Has to go perpendicular. This also must go perpendicular direction. Why? Because if they are not meeting a surface perpendicular direction or not emanating from the surface in perpendicular direction, then let us consider a very interesting situation here, that we are assuming that they are not perpendicular. Lines of forces, once directed this way, one line of force coming this manner, another line of force going this manner. So what will happen? Two things going to occur. Firstly, they are intersecting each other. That is not possible. Logically, it was not possible. They will intersect. Second problem is the strength. Suppose this electric field magnitude is E over there. Then it has two components in its, this E can be directed this manner, can be directed in perpendicular direction. No, so perpendicular direction means you can take, if you have taken this way, one field line may be directed this way, component may be directed this way, another component may be directed this way. This E may have component EX and EY. Then what is happening? Due to this field strength inside the conductor, charges will move along the direction of field. So in electrostatics, we have started current electricity. Charges are moving also. It is not possible. Because along field line, a charge will move. So if you say that it is not perpendicular to the surface, then it is component. One this manner, the other one this manner. Maybe other situation also there. But due to this field strength, they start moving along the conductor. This is a conductor. We are considering conductor only. They will meet the surface of conductor or emanate out of the conductor in perpendicular direction. Other direction not possible. If you think that, then it is contrary to the principle of electrostatic, where charges are static. They start moving. Each field is directed this way. So situation does not arise. From all these discussions, I am going to tell you the rules of drawing electric field line. Just whatever I have discussed with you, based on this, I will be telling you what are the rules for drawing electric field lines. Field line begins at the charge and ends either at the charge or at infinity. This I told you earlier also, just to remind you. In the nearby space, surrounding space of a point charge, they never terminate unless one positive or negative charge is there. Closer field lines indicate a stronger field. This is very important. Let me explain this part. Closer field lines indicate stronger line. What is the meaning of this thing? That suppose you are taking a positive charge here, plus Q, and drawing field lines due to this. As many as possible we will draw. Then I will explain how closer field lines indicate stronger electric field in a region of space. Just a few more we draw. Like this. They will be symmetrical. In my drawing, one is coming smaller, other one coming bigger. It doesn't mean that they are, we are thinking about asymmetrical field. Now, this is enough. Imagine we are keeping one unit area at this point and another unit area, the same unit area at this point. What we have kept over there? It is perpendicular to the direction of lines of forces. This area is closer to the field, more number of lines of forces passing, closer to the charge, and more number of lines of forces passing through it. Electric field is stronger also. At this point, if we have done, electric field is stronger here. Electric field is weaker here. So, more the number of lines of forces passing through this unit area, more the strength of electric field over there. So, first observation is number of lines of forces proportional to the magnitude of charge. This I showed you. This I mentioned earlier. And here another observation we are doing, that more the number of lines of forces passes through a point, stronger is the electric field over there. That's why I've added this point. Closer field lines indicate a stronger field. Okay? In fact, strength of electric field at a point will be decided depending on this fact. It is number of lines of forces crossing this unit area. This unit area, how many lines of forces passing through it? This is the measurement of electric field strength over there. This we'll learn in Gauss law. But here, just remember, closer field lines means stronger electric field over there. Number of lines depend on the charge mentioned earlier. Field lines should never cross each other. Told you earlier, electric field and field lines are tangent at the point where they pass through. Told. Field lines symmetric. I told you so many times. Whenever you are drawing field lines, it must be symmetric. Don't be influenced by my drawing that one is small, the other one big, not like that. When you will draw symmetrically. Okay. I'd like to discuss some problems based on electric field lines. But once we recap all the topic, it will be better. Due to positive charge, field lines radially outward. Due to negative charge, field lines radially inward. Due to two isolated positive charge, field lines will be in such a way that they're exerting lateral pressure on each other. Due to one positive and one negative charge. And another thing I'd like to say, when two positive charges are there is a repelling point, they are repelling each other. There will be a point where no electric line of force can pass through. That will be referred as neutral point. So due to one plus q, another plus q charge, neutral point will be here. But if we take 1 plus 2q, the another plus q charge, neutral point will not be exactly midway between two charges. This I have explained. It will be in what direction? It will be near to the weaker charge. It will be near to q. This you have done before. So neutral point you will get near this plus q charge. In fact, neutral point concept also I have told you, and due to 1 plus q, 1 minus q charge, neutral point you will be always getting that outside the line segment joining two charges. Okay. Similarly, 1 plus 2q and 1 minus 2q charge is given. There also the electric field will be 0 at a point outside the line segment joining two charges. Clear? Now, what I told you here, very important point, that strength of electric field is proportional to magnitude of charge and number of lines of forces or field lines also proportional to magnitude of charge. There is a scope to learn here that 1 plus 2q, 1 plus q charge is there. How to compare these two charges? Why this charge will be double of it? Very easy to understand. Here you count number of lines of forces. It will be 1, 2, 3, 4, 5, 6, 7, 8. And here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. See? I told you these are imaginary lines, no? So lines will be taken in such a manner that due to plus q, if 8 lines of forces are coming out, due to plus 2q, 16 lines of forces will come out. What will happen in this case? Is it same for 1 plus 2q and 1 minus q charge? Yes, similar is the situation. You just observe this picture here that minus q. How many field lines are entering into it? Just let us count one by one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay. So due to minus q, field lines entering into it is 14. So due to plus 2q, how many will come out? Due to plus 2q, 28. These 14 are there. If you count these, you will get 14 more lines of forces. So 28 lines of forces are coming out of this charge 2q and 14 entering the charge minus q. So this will help us, field lines will help us to compare the magnitude of charge. Okay. Now I have just putting this question forward for you. Can you compare these two charges? I mean, what is the ratio of q1 and q2 here? Can you find it? Yes, we can find. So this q1, how many charges are terminating here? 1, 2, 3, 4, 5, 6. So on this q1 charges are terminating. So make this observation, q1 is negative and number of lines of forces entering charge q1 is equal to 6. What about q2? Q2 if you find, I mean these six lines of forces are there already. In addition to this, these three, again these three. So 12 more lines of forces are there. Here it will be 12 plus 6, that is 18. You understand? Those 6 are coming from Q2 only. As lines of forces terminating here, Q1 is negative. And lines of forces emanating from Q2, so Q2 is positive. This you should understand. Okay? So Q1 positive and Q2 negative. Somebody asked you to find the ratio. You can find the ratio easily, that Q2 by Q1, because it depends on number of lines of forces, is going to be equal to 18 by 6, that is 3:1. But this is mod Q2 is to mod Q1. Actual ratio will be there in many competitive exams. I have seen questions like this. They are asking this ratio, Q2 by Q1. What is its value, Q2 by Q1? Q2 by Q1 value will be minus 3 by 1. Why? Because Q1 is negative and Q2 is positive. Let us do another example here. Can you compare quickly these two charges? I just help you. How many entering here? No. How many emerging out here? 1, 2, 3, 4. So NQ2 equal to 4. What about NQ1? Let us see. Q1 how many? These 4 are there. These 4 are there. Then in addition to this, 6, 4, 10, 14 and these 2, 16. So Q2 by Q1, if you take mod Q2 by mod Q1, this is going to be 4 by 16, 1 by 4. But lines of forces terminating at Q1. So Q1 is negative. Q1 negative means Q1 is negative. What does it mean? That Q2 by Q1, this ratio going to be equal to minus 1 by 4. Clear? This we can compare in all these diagrams. So I'll share this worksheet with you so that you can practice on your own. These two is your work. You complete these two in the assignment. Okay? I mean, compare these two charges. One is say Q1 here and this is Q2. What is the ratio between these two charges? Here also you take this one Q1 and this one Q2. Just by counting lines of forces, you determine the ratio between Q1 to Q2. Now, suppose there is a hypothetical situation like this where 3 points ABC taken in the region of space where lines of forces are like this. Maybe there is a metal conductor, lines of forces are drawn in this manner. You have to compare the field strength between among these 3 points EA, EB and EC. This is very simple because lines of forces, closeness of lines of forces will tell you the stronger field. So here lines of forces are more close than that the point B, the point A. At a number of lines of forces closer than that the point B. So what going to occur there? Electric field will be strongest at C, then at A and then at B. Okay, this is just by seeing the diagram, I mean lines of direction of electric field lines and its number, you can decide which case the field will be stronger. Now, what are uniform and non-uniform electric fields? Uniform and non-uniform electric field, just clear from the name only. Uniform electric field is that where strength of electric field will remain the same. So E is equal to a constant for, I am writing E vector is equal to a constant for uniform electric field. What do you mean? It means the magnitude and direction of electric field strength will remain the same at all points. How to represent that? It is not possible by drawing lines of force the way we are drawing so far. Those lines of forces will be represented by drawing equidistant parallel lines always. Okay, these are lines parallel to each other and distance between them is also a constant. So if you draw equidistant parallel lines, here E will remain the same. E is equal to a constant. E at this point, E at this point, everywhere at this point, same magnitude and direction. But if the field lines going this manner, like this, here strength of electric field will not remain the same at all points. E is not equal to a constant. E is not constant over there. Okay, understand the meaning of uniform and non-uniform electric field. This should be represented by drawing equidistant parallel lines, and here obviously they are not equidistant parallel lines. In the forthcoming chapters, topics, we need the concept of this kind of representation. So if you take 3 points A, B and C this manner, then also EA will be equal to EB equal to EC. Now the question is, what will be the strength of electric field inside a conductor? Does it exist? Electric field line never pass through a conductor. This is one of the property. Electric lines of forces or field line never pass through a conductor. So E will be always equal to 0 here. Inside conductor, electric field strength will never exist. E is equal to 0 if this is a conductor. What is the reason? Because no line of force can pass through a conductor. So actually, existence of field line is the existence of electric field strength over there. For non-zero field strength, at least a line of force will be there. Okay. Now let us discuss some problem which appeared in previous year's JEE papers, like few electric field lines for a system of 2 charges fixed at 2 different points. These lines suggest that mod Q1 greater than mod Q2, all these things. This we can easily solve because this kind of problem we have seen before. From this Q1, how many lines of forces are coming out and how many entering at Q2, that we need to find. Okay. So it is quite obvious that Q2 is negative here and Q1 is positive. From Q1, how many lines of forces are emerging out? 1, 2, 3, 4, 5, 6, 6, 3, 9, 10, 13. So if we write number of lines of forces emerging out from Q1 equal to 13, then number of lines of forces terminating at Q2 will be 3, 3, 6, 7, 9. Okay. So Q1, mod Q1, actually Q1 is proportional to 13, Q2 proportional to 9. So Q1 by Q2, their magnitude will be proportional to the number of lines of forces. It will be 13 by 9. Clear? but Q2 is negative. Q2 is negative, so Q1 by Q2 ratio will be negative. But they have asked only comparison of their moduli. Mod Q1 by mod Q2, you got 13 by 9, which is larger than 1. Therefore, mod Q1 is greater than mod Q2. Clear? So just by counting, but this one, as I remember that multi-option correct was there. Let's see what other option can be correct. So obviously this option is incorrect. This one not correct. This one correct. At infinite distance to the left of Q1, field will be 0. No. This I'll take some reference from previous classes where field strength will be 0 near the smaller amount of charge. So smaller amount of charge is Q2 here, not Q1. So field will be 0 near Q2. But it is not on the line segment joining these two because Q2 negative. So it will be on the right side of Q2. At this point, electric field will be 0. So this is incorrect, this one correct. Option A and D are correct. This question came in 2001 JEE, IIT JEE paper, 1 mark question. You can decide quickly which one will be the actual diagram. Multi-option correct, no. This was only one option correct, I remember. This one not possible. Why this one not possible? Because 3 charges equal magnitude Q were placed at vertices of equilateral triangle. All are Q. These are Q only. All Q charges are there. So they are showing this is the direction of line of force. That line of force direction was given this way. So firstly, no direction given. And it is shown that it is extended from this charge to this charge. Electric field cannot go from a positive charge to positive charge. So this situation impossible. Is this situation possible? No, you can see the lines of forces have intersected. Many points are there like this. So this is also impossible. Is this a possible situation? This one is possible because lines of forces are exerting lateral pressure on each other, which I have discussed with you earlier. And another thing is that they don't intersect. They are separated, they don't intersect, and they are coming out. You just put arrow direction, then it is perfectly alright. Okay? So this is correct option. Is this correct? No. Lines of forces never form closed loop. So this one also incorrect. Only option C is correct over there. Another 2015 JEE main question. Long cylindrical shell carries positive charge sigma at the upper half, negative charge minus sigma here. The electric field line around the cylinder will look like what? So cylinder, this half is positively charged. This half is negatively charged. Your problem, which situation is correct? Lines of forces quite obvious. All lines of forces, they emanate from positive, terminate at negative. So situation B does not arise. Is this possible? A, we did not think that from positive it's coming, negative it is terminating. And here one line of force is coming out. So this situation also not possible. How can this come out? This is not possible. Is this possible situation? From positive they are coming out, from positive coming out, from negative entering, but the lines of forces from positive to negative, just I told you, in a region, if a positive charge there and a negative charge there, lines of force can never go to infinity. So line of force has to go from positive to negative charge. Here, they cannot go to infinity. So this is the ideal situation. Charge is coming from positive and terminating at the negative charge. So situation D is possible. Okay. In this context, I'd like to discuss another problem where two charges Q1 and Q2 are situated in such a manner that angle between the lines of forces coming out, two lines of forces are given here 60 degree and this one given to be 90 degree. You compare Q1 and Q2. Mod Q1 by mod Q2, what is the ratio here? Okay. This comparison can be done quickly if we just remember a very simple fact that lines of forces from a charge, isolated charge, can be drawn isotropically. I mean, they extend in all directions. Symmetry should be there. So, if this one 60 degree, how many lines of forces can we get this manner? 60 degree is given here. Total angle 360 degree about the point when these lines of forces terminating at the charge. So, from Q1, we can draw for Q1 only 6 lines of forces. 6 lines of forces, let us draw now. One going this way, another going this way. This is 60 degree. Then another one going like this. Going like this. Going like this. Wait a minute. So for this Q1, if we draw electric lines of forces, total angle Q1 is at the center. Total angle about Q1 will be 360 degree. So how many lines of forces can come out of it? 6 lines of forces that you can draw. Okay. What is the angle between two conjugative? That if you produce them, they will meet at an angle 60 degree. So this one 60 degree. Between these two 60, total 60. How many lines of forces can come out of Q1? This is going to be 6. Similarly, if you take Q2, how many lines of forces can come out? These two lines of forces, they make 90 degree. So in total 4 lines of forces you can draw from here. So those 4 lines of forces only possible in Q2 is going to be equal to 4. It is because of symmetric property of number of lines of force. Symmetric property of electric field line. You cannot get more than that. It is not possible. So 90, 90, 90, it will make 360 here, 4 lines of forces, and here 4 lines of forces. Actually in this case they will be meeting here. They are not coming out. They will be meeting the charge. Okay. They are meeting the charge Q2. So number of lines of forces meeting the charge Q2 is going to be equal to 4. Clear? So NQ2 4 and then NQ1 equal to 6. NQ1 that divided by NQ2 equal to 6 by 4, 3 by 2. It is greater than 1. So Q1 magnitude, if you consider the magnitude of Q1 with Q2, this thing is greater than 1, then mod Q1 will be greater than mod Q2. Clear? Thank you. I hope you have understood.